Hey, welcome to Dinsmore Racing and a little training video we're going to have here on engine terminologies. We have a cutaway of an engine here that we've done, and we're going to look at the components inside of it and discuss the terminologies that we'd have, TDC and BDC and scavenging, and some of the areas that we hear when we're going through a training. We're not sure what they mean. So this little cutaway in this video is going to describe some of those terminologies and where you would hear them and what they mean, and give us a little bit more knowledge of the cylinder and the piston and the valve train of an engine and how it works and how it operates, and things that we would need to know to be a technician and work on these things. So welcome to this video and enjoy it. We have our cutaway we've made here of an engine, and we're going to discuss the 4 strokes that go on. We're going to discuss our intake and our exhaust stroke. We're going to discuss our power stroke and our compression stroke as we go through what happens inside of this engine. And then we're going to discuss some of our terminologies that we have. And the first thing we'll look at is terminologies of TDC and BDC. The first one we're going to look at is top dead center. And top dead center is our uppermost travel of our piston and its bore. When it gets right to this point at the top here, and it starts rocking back and forth a little bit, right there is TDC. That's the uppermost travel the piston can make, top dead center. At this point here, the piston has to stop, change direction, start moving back down. And as it goes down through its stroke, we're going to get down here to the bottom, and right there we see it changes its position again. And that's BDC, bottom dead center. And in these two areas we look at of what happens in the events. The piston comes to a complete stop, changes direction, and starts heading back up the bore. When we look inside of our chamber, what happens from TDC to BDC as we're traveling downward, so from top dead center to bottom dead center, as this piston is traveling downward, we define what is called swept volume. And that's the amount of air that can be brought in to fill this area in here. And now that's going to depend on our piston diameter, the bore of the cylinder, and the stroke. How far this piston moves in here will define the swept volume of the cylinder. It's also going to define the displacement of the engine. But this swept volume becomes important because that's how much air, fuel mixture we can bring in, aspirate into the engine. We also get swept volume going up on our travel. We take what's in here and we compress it into this hole. We're still taking whatever volume we have, pushing it into a small area, and that's going to define our compression ratio when we're done. So the swept volume going down is going to define how much air, fuel mixture we're bringing in, and the swept volume going up is going to determine how much volume and cc's or cubic inches of air we have in here, fuel mixture, that we are going to take and crush into this small little place to define our compression ratio. So we will look at both swept volumes as we're going through this. As we get in here a little farther, we're going to look at our different strokes that we have on our engine. And we can see our components in here. We have our rocker arms over here. We have our intake rocker and our intake port going in. Our intake port comes down through here. Here's our intake valve. We have our exhaust port over here, which our exhaust gases are going to travel out. So we'll look at all these ports. We'll look at our rocker arms as they start moving. Intake for the intake stroke, exhaust for the exhaust stroke, because that's going to determine when our valves are going to open. And we'll get that in relation to our 4 different strokes that we're going to talk about. As we're looking at this engine, the first stroke that we're going to look at is my piston's at top dead center here, and this intake valve begins to open. At that point there, we're going to begin what's called our intake stroke. And we can see this rocker arm moving down, we can see this valve opening, and we can see our piston traveling downward in the bore. As that's happening, the engine is bringing air in through the port around the valve and filling this area in here with clean air fuel mixture with oxygen molecules in it. So we have oxygen rich air fuel mixture that we can ignite with the spark plug when we get to TDC again and have our power stroke. So we fill this area up with our air fuel mixture through our swept volume of what we can aspirate and bring in. As we bring that all in and we get the BDC, the piston will stop, as I said, and change direction. And as it changes direction and travels upward now, our intake valve is going to go closed. As it goes closed, the piston is now compressing the air-fuel mixture that's in here, and it's crushing it all into this small little space as we get to TDC. And at TDC, it's crushed all that air-fuel mixture into that little spot, giving us our compression ratio of our engine. And at that point, we're going to take with a spark plug and ignite that air-fuel mixture on a gasoline engine. If we're talking a diesel engine, it's going to be compression ignition, and we're going to inject diesel fuel in there. But we will ignite that air-fuel mixture. At that point, because it has oxygen and fuel mixing, it's going to ignite and start burning. And what happens when it starts burning? The gases expand very rapidly, and they push on the top of this piston and put a force on the top of here. And it forces that piston back downward to our power stroke. And as we get partway down through our power stroke, our exhaust valve here is beginning to open. We can see our rocker arm moving down. Our exhaust valve opens, and we will start our exhaust stroke. After 90 degrees of crankshaft rotation, we lose the leverage that's on the crankshaft. So after that point, we can open our exhaust valve because we're no longer really making horsepower with it, because the connecting rod on the crank has gone over its 90 degrees and we're losing our effective stroke. So we'll start opening our exhaust valve after that point. We've captivated and used all the heat energy that we can, force on top of this piston, change it into kinetic energy, force the piston downward, which in turn reciprocated the piston and rod and turned the crankshaft in the engine for the power that we're going to need to put out of the flywheel to drive whatever we're driving, whether it's a clutch and a transmission, or electric motor, or a generator, or a hydraulic pump. Depends what the application is going to be. So we force that down, we turn that into kinetic energy to turn the engine. These power gases that are in here from combustion, as they're expanding, keep pushing that piston down, and we get to the point the exhaust valve opens. We take some of that pressure that's in here still and help the exhaust gas to start to get expelled through the port. They get pushed out of that port and they get moving out of it. And as the gases are moving out of this port, our piston starts moving upward in its travel now. We've gone from BDC and we are heading towards TDC. All the time we're helping push these exhaust gases out of this port. And as we get closer to TDC, we're forcing those gases out, cleaning all the burnt air-fuel mixture out. It's got no oxygen left in it, so it's of no value to us. We're going to send that out of this port, and we're going to get rid of it. And that's getting rid of that exhaust gases now, and they're out. At or near the top here, we're going to see this other valve open, and we're going to talk about that in a minute. This here, we've got rid of our exhaust gases. We're going to begin our intake stroke again. So we start our intake stroke, we take our air-fuel mixture in, we start our compression stroke, we come up and compress the air-fuel mixture, one revolution of the crankshaft. We have our power stroke, we're going to force the piston back downward. And as we get to the bottom, we have our exhaust stroke, which now we're going to get rid of the inert gases, the burnt fuel that's in there, no oxygen in it. That's 2 revolutions of the crankshaft, 720 degrees, 4 strokes to complete a cycle on a 4-cycle engine or a 4-stroke engine. That's why we call them 4-stroke or 4-cycle, to get through that. I'm going to get in here a little more in depth and look at how these valves overlap. We're going to discuss that a little bit of trapping of our compression in here and what becomes important in the power stroke to how we can get more and more horsepower in that out of these engines, and what we do today in a lot of our engines to increase power. Today we use variable valve timing and stuff. But if we look here on my intake stroke, my piston's going to start moving downward and this valve's going to start open. We can see this valve coming off its seat. It's coming off its seat. It's bringing the air fuel in and filling this chamber. As we get down here to the bottom, it stays open. It stays open past the piston's moving upward now. This piston, if you look right here, it starts moving upward. See right there? And as that's moving upward, my intake valve is still open. Well, because when we look at inertia and what happens in inertia, something in motion wants to stay in motion. So these gases that are traveling in here fast, the air intake, air fuel mixture that's coming in here fast, it keeps moving and it wants to keep on moving and it wants to keep coming past this valve. So even when this piston is coming up a little bit, I'm still charging that cylinder a little bit with air fuel mixture. What is more important is that this valve has to touch that seat and seal against that seat before I can start compression. If I shut that valve now with my piston way down here, I got all this area for a compression stroke, and it takes horsepower away from the engine because now my engine becomes a compressor more than anything else. So in camshafts, what we do, if we want to have a lot of low end torque, we'll close this valve early and get a lot of compression soon. If I want to have high end horsepower, then I close this valve later. And our variable valve timing engines today will do that. This engine is not a variable valve timing engine. So this valve is going to close at a specific time every time through its cycle. And I've put a little mark down here in the cylinder you can see. And that is the distance between bottom dead center and the closing of the intake valve. So we have that much piston travel before that valve closes. What that does is that allows that piston to come all the way up there before it starts turning into a compressor and starts slowing down the engine and making the engine work to compress the gases. A lot of today's engines are what they're doing is what's called a Miller cycle, and we will variable valve time this engine as we're traveling down the highway. We may variable valve time it all the way up to here if it needs no horsepower. We'll keep doing that so we don't turn the engine compressor. We get better fuel economy. If it needs horsepower, the variable valve timing will close this valve sooner and give us the torque we need. If I'm pulling away from the corner, I may close it here if I'm just driving around in a grocery getter and close it down here to the point that I get lots of bottom end torque. But this engine will quit making horsepower at 3,000 RPM. If I close it later, it's going to make horsepower higher in its range. So in performance engines, we close these valves later. We do that so that we have higher horsepower at the top end. As we are increasing our air movement in, we increase our air velocity past our valve, and we can charge that cylinder with the correct amount of air-fuel ratio that we require to have the burn in here proper to make the horsepower that we want out of an engine. And as we're traveling upward in our compression stroke and we get to the top, we fire our air-fuel mixture in here and force this back down. And as we're forcing it back down, we can see here this exhaust valve is just coming off its seat. I put a mark here in the cylinder. See that little mark right there? Right there? That's where the exhaust valve is just coming. And you can see that exhaust valve here just moving off its seat. At that point, my pressure that's left in here from combustion is going to start traveling out past this valve and get the air movement in this port. As it gets the air movement in the port and I travel down farther, that pressure is still going out there. I still have a little bit of pressure in here. It's going out and it starts all those exhaust gases moving. As I start moving upward, now my swept volume, my piston, is going to push those exhaust gases out and clean this cylinder right out. As we keep traveling through our exhaust stroke here and we get up near the top, this becomes where we have interference fit in our valves. We have really tight tolerances down in there. That piston is actually chasing that exhaust valve up the port. But look over here, watch this valve. It's coming off its seat. Well, I'm not at top dead center, I'm a long ways from top dead center here. And we can see both those valves at that point are rocking on their seats. This is called valve overlap. This is where both valves are open the exact same time, and we do that for a couple reasons. First of all, this exhaust valve opens up during our exhaust stroke and it gets a lot of heat put into it. We can have well over 800 degrees, high output engines maybe 1400 degrees of temperature put into that valve as it comes off its seat. The only way this valve is going to cool is by some fresh air coming by it to help cool it, or when it touches the exhaust seat to allow the fins on this air-cooled engine or the water that would be in here on a water-cooled engine to pull the heat away from that seat and pull the heat out of that valve. It wants to pull the heat out of there and get that valve to cool down. We don't really think about it or realize, but if this engine is running at 6,000 RPM, that valve touches that seat 50 times a second. So it doesn't have much time to cool down. And for you guys that are playing with your street bikes and that, and you're running to 12,000 RPM, it's 100 times a second. It's not getting much time to cool down. So we require this overlap of fresh air coming in to help cool that valve. The other thing it helps do is when this air-fuel mixture is coming in, it helps cool the top of the piston that's got hot from combustion. Because our combustion gases in here are extremely hot, we can see pressure and temperatures on those combustion gases. We can see pressures of 3,000 psi or higher on high output engines, and we can see temperatures in here of over 1,000 degrees during combustion. So this air coming through here and this valve overlap is going to cool the top of this piston also. Remember that something in motion wants to stay in motion. So if I have exhaust gases going out here, they are pulling on this here. As I open my intake valve, that's going to help start the intake air moving in, because at this point here we create a little vacuum in here, a void of pressure, which helps a little bit of the air come in here if we get the overlap right. And that becomes very important in performance cams, how I can get those two valves to open at the correct time to not have pressure being pushed up here by the piston, but allowing my air to start moving in here and get pulling in the cylinder again by the little bit that happens on the exhaust valve. And we put headers on these engines and everything else to help pull that air out of here, to put a little more vacuum on here to try and pull that intake air in and get the intake air moving down the port and coming in past there. So the intake air starts moving down the port, coming past the intake valve, cools the top of the piston, cools the exhaust valve, cleans all the exhaust gases out, scavenges all the last of the exhaust gases out, and starts filling this with nice clean oxygen molecules that we require for our next burn. And then as we go, we see our exhaust valve is just starting to close there. We are well down our bore off TDC. Our intake valve is opening, and it's going to continue opening till past bottom dead center, and then it's going to start closing as my piston's moving upward. Still some air fuel mixture is going to come in because that air velocity is moving, but as we get up here it's slowing down and slowing down, and at that point there I am going to take and close my intake valve and begin my compression stroke all over and compress whatever's in here into this small area for my compression ratio, and have that all ready for my next spark and my next power stroke, so I can go through this all over again. During these cycles on our piston we have our rings that would fit in these grooves. We have our oil control ring, our second compression ring, and our first compression ring in here. The first compression ring is trying to seal the cylinder and stop all the compression gases from leaking by it slowly. It's trying to stop the combustion gases from going by it when we have our combustion and our burn in here, and it's trying to seal that all off. The second ring here is a backup for compression. Hopefully it's not catching any compression. If it starts catching compression, then this top ring is leaking and we have problems. But these seal against our cylinder wall in here, and we pull some of the heat of the top of this piston. We were talking about the heat. This top ring up here, when this piston is hot and going down under combustion, that ring is being pushed into this seat with tension into the ringland area, and that tension, that ringland, is going to allow that ring to start conducting heat out of the piston through the cylinder wall, out through the fins that are here to help cool this piston. 20% of the cooling of the piston is done through the rings, pulling the heat out of the cylinder. So the rings are important in sealing the compression gases, sealing the combustion gases, and help cool the piston in here. Our second ring is helping aid in our cooling. It's also helping aid in the oiling of the cylinder to make sure that we get a little bit of oil up in here to lubricate this ring, but not much. Our third ring in here is called an oil control ring, and that oil control ring is going to control any oil that is getting pushed up. It's going to take the excess of oil on, keep it on our skirt here for bearing surface during our combustion and our compression strokes, the loading that goes on the piston, and maintain that. So the rings provide a important role in sealing these combustion and compression gases that are in here, and making sure that we don't get oil into the top of the cylinder to cause the engine to start burning. Oil is one thing. High hydrocarbons and emissions is a problem, and oil takes away from our horsepower and robs away, and we start coking up with that. So we want to make sure we don't get oil up into our top end, but we want to be able to seal the gases that are in here so we can have the proper combustion and compression stroke on it. So that's our 4 different strokes of our engine. That is our terminology of top dead center and bottom dead center. Now remember, at top dead center, anything that happens in the piston moving to the bottom is after top dead center. The piston's moving downward, so it's after top dead center. And anything when the piston is moving upward is before top dead center. So we use a code on that as BTDC, before top dead center. Or some manufacturers will try and confuse you and put after bottom dead center, ABDC. And so these terms are there when we're reading our specs books and that's what that terminology means. So 4-cycle engine, 4 strokes we go through. The top dead center, bottom dead center is our terminology that we're going to use on there. Valve overlap is when both valves are open at the same time, and we use that for scavenging of air to help cool the piston, cool the exhaust valve, and bring fresh air in here and get rid of the last of the exhaust gases. Happens during scavenging. And different camshafts will have different scavenging on it. Depends on the engine. Turbocharged engines don't have as much scavenging as we're forcing the air in. So a few different things that we can have there. So that's our terminology on engines and what happens through our 4 cycles and 4 strokes, and how the valve train operates inside of the cylinder head in relation to where the piston is and the timing of the piston. That this piston and this valve train that's in here is timed to the crankshaft, and when we take engines apart we have to make sure that we time the camshaft to the crankshaft so that the moments that this valve opens is proper to the piston location. If we put the cam in wrong, then it's going to open the wrong spot. Sometimes we can have valves hit pistons. We can have all sorts of little issues happen there if we open them at the wrong time. So make sure whenever you're working on an engine that you are checking that valve timing when you're putting engines together, with a timing belt or a gear drive, which is for a different day when we'll look at those components.